All right, ladies and gentlemen, today's class recording has started. So, over the past couple months, we have been talking about atoms and the structure of atoms, and then in the last unit, before we took exams, we talked about the periodic table, and we talked about nuclear fusion and how all these atoms get made. But if you look on the periodic table, right, there are 118 different elements. Each of them is unique, different from all the others, but I bet if we went around this school, it wouldn't take us too long to find more than 118 unique things. Following me? All right? Meaning that there has to be some way for those 118 atoms, those 118 elements, to arrange themselves in more than 118 different ways. Yes? And that's the gist of bonding. What we find is that these atoms have the ability to join together in a way to make something new that has a different set of properties than what those elements had individually before they joined together. And so this unit is about how those atoms join together, what happens during that process, and what are the different ways we can get combinations of those elements to make these new unique substances. Okay? All right, so let's first talk about chemical bonding. Okay? By definition, a chemical bond is an attractive force that holds atoms together. That's how we're going to define a chemical bond. The formation of bonds involves energy, and more specifically, sweet. So, do you guys have like the? Are you? Do you have the beginning of the?
I do.
Okay. So. Says the formation of chemical bonds involves energy, and that's true. But before we go any further, we have to do a quick pop quiz. Okay? So, baseball. Okay? We've done this quiz before. We'll probably do it again, but here we go. You ready? Why does that happen?
Gravity.
No.
Oh. Potential energy.
Gravity is how it happens. Why it happens is potential energy. The ball starts with a lot of potential energy. Do things like having lots of potential energy? No. They will find a way to reduce the amount of potential energy they have and turn it into other forms of energy. Here, what did the baseball turn its potential energy into? Kinetic energy. Gravity was how that happened, but why it happened was to reduce the amount of potential energy it had to turn it into other things. Good? Okay. Same thing is true with bonding. Bonds between atoms will form if those atoms have a lower energy together than when they were separate. And one thing I guess I should add in here, right, instead of just a lower energy, right, we probably should put potential energy in that space. Atoms will join together and form a bond if they have lower potential energy together than they did when they were separate from each other. Okay? Good with that idea? As a result, bond formation is generally what we call an exothermic process. We've run across that word already once in this class, right? What does it mean when we talk about something being exothermic? Go ahead. Heat is being released, right? Again, I should probably change this here. The products have less potential energy than the substances that we started with. But if potential energy goes down, what has to happen? Does it always have to be kinetic energy that goes up? No. But something else, some other kind of energy has to go up. What do we call that concept? Conservation of energy, right? If potential energy decreases, another form of energy has to increase, because what has to be true about the total? The total has to stay the same. That's conservation. That's one of the things that we use and apply to a bunch of different situations. It applies here. Now, as far as how it happens, now we start looking at the structure of an atom, particularly the valence electrons. Valence electrons is our concept that we've introduced before. Where do we find valence electrons in an atom? Highest energy level, or if we're talking about the atom, where in the atom are we talking about? Farthest from the nucleus, the outside edge. That's where we'll find our valence electrons. Those are the ones that we're concerned with when we're talking about how bonding happens. Why does bonding happen? Because atoms are trying to get rid of potential energy. How does it happen? Through valence electrons. Good? Okay. If we're concerned about valence electrons, we have to have a way to keep track of them. So that starts with something that we call a Lewis structure. Lewis was a scientist. You don't need to know anything about him. You just need to know that these structures are named after him. All right? Now, before we start drawing things, I'm going to do some stuff over on the sideboard over here that is from previous chapters, and I hope we remember it. Okay? So, if you look on your outline, and hopefully the recording will pick this up some far away. If you look at your outline, the first element that is listed under Lewis structures is what? Lithium. Okay? So, actually I should do it up here so that people watching the recording could actually see what we're writing. Okay? All right. Oh, that's if some people actually watch the recording. All right. Magic pen. There we go. So the first element listed on your sheet, and if you want to write this, there's a little bit of space underneath the word lithium on your outline. You can write this here if you want to, but it's not going to be totally necessary, okay? We are going to write some electron configurations. All right, so electron configurations show us where electrons are located around the nucleus, especially which orbitals those electrons are located in, right? So, first, lithium. How many electrons do we have to keep track of? 3. That's lithium's atomic number, right? Okay. What's the first orbital that always gets filled? 1s. So we start off with 1s, and we use an exponent, or a superscript, to represent the amount of electrons in that orbital. How many electrons can the 1s orbital hold? 2. So we start off with 1s2. Okay? Lithium requires that we place 3 electrons, right? We've got 2, so we go to the next orbital. What's the next orbital to get filled after 1s?
2s.
2s. How many electrons are in that 2s orbital?
1.
Just 1. Okay? So, for lithium, what's the highest energy level that has electrons in it? The second level. How many electrons are in that second level? 1. So how many valence electrons does lithium have?
1.
1 valence electron. Okay? Good there? Alright. Next on your list is oxygen. Yes? Okay. How many total electrons does oxygen have? 8. That's its atomic number, right? Okay. Where's the first place that electrons go? 1s. How many electrons? 2. Okay. Next orbital that gets filled is what? 2s. How many electrons can it hold? 2. Do we remember the next orbitals?
2p.
2p. All right. How many 2p orbitals are there? There are 3 2p orbitals, and each one of them can hold a total of 2, so that would be a total of 6, right? Although in this case, how many electrons do we only need to put in there? 4. Okay? Now, here's where we have to be a little bit, make sure we understand what we're talking about. What's the highest level that has electrons in it for oxygen? Not 2p, that's an orbital. What's the highest level? 2 is the highest level. Some are s orbitals, some are p orbitals, but that's still the second level. Yes? Okay? How many electrons are there in the second level? There are 6 total. These are in the second level, but those are in the second level as well. So how many valence electrons does oxygen have? 6 valence electrons. Okay? Good so far? Okay. Next on your lists, I believe, is fluorine, right?
Yeah.
How many total electrons does fluorine have? 9. So this one's going to be pretty easy, right? We already know that the first 2 go here. The second 2 go here, right? And we discussed before how many electrons can fit in the 2p orbitals total. 6 could. Oxygen only had 4 of the 6 spots full. Fluorine only has 1 extra electron. So we go like that. For fluorine, what's the highest level that has electrons in it? 2. How many electrons are in that highest level? 7. Right? Some are in S, some are in P, but there are 7 total. Fluorine has 7 valence electrons. Good so far? Okay. Next one on your list, chlorine. Okay? How many total electrons for chlorine? 17. Okay? The first 2 go here. The second 2 go here. The next 6 go here. Now we're up to how many? Up to 10. Okay? Do we remember what's the next orbital filled after 2p?
3s.
3s. Okay. How many electrons go into 3s? 2. Do we remember what comes after 3s? 3p. 3p, right? Again, how many electrons could fit in the 3p orbitals? 6 could, but 2, 4, 10, 12, how many do we only have to put in there?
5.
We only have to put 5. So now for chlorine, what's the highest level that has electrons? 3. How many electrons are in the third level? 7. So chlorine also has 7 valence electrons. Is that a coincidence?
Yes.
Look at fluorine and look at find fluorine and find chlorine on your periodic table. Where are they? They're in the same family, right? All elements in the same family have the same number of valence electrons. Okay? All right. Is this good? Do we remember this? Okay. This is a lot of work for starters, right? But we want shorthand representations of this important information. This all started back with the last statement on this slide that says bonding deals with valence electrons. So, we write Lewis structures to show the valence electrons that an atom contains. A Lewis structure consists of the symbol for the element and a dot or dots to represent the valence electrons. So, going back to the first element we did was lithium. How many valence electrons does lithium have? 1. So this is what its Lewis structure looks like. You don't have to write the box, you just have to write the symbol, okay? And then 1 dot around the outside to represent the 1 valence electron.
Doesn't matter where.
Okay, good questions. Does it matter where? No, it does not matter where you put these valence electrons. It does not matter how they are arranged as long as we have the right number. That being said, what you will find as we go through this is there is a way that we usually show this, that we usually show the valence electrons because it helps us with the next step of this process. Okay? All right, the next element that's written on your outline is oxygen. How many valence electrons did we say oxygen had? 6. This is what the Lewis structure for oxygen looks like. Generally speaking, we look at the symbol as having kind of 4 sides, right? Sort of like a top. Come on. Oh, it's not what I wanted.
Spoilers.
I know, sorry. It has like a top and a side and a bottom and another side. If we look, usually we'll put like 2 on the top, 2 on the bottom, 2 on the side, 2 on the other side, at least as much as we can. How many dots should there be? 6. All right. Next, spoiler alert, right? What did we say about the number of valence electrons for fluorine and chlorine? 7. They both have the same number of valence electrons. So their Lewis structures look the same, except that one has F in the middle and one has Cl in the middle. Okay? Doesn't matter which side those dots are on. Okay? No, it really doesn't. Okay? Yeah, it really doesn't matter where the open spot is. As long as you have those 7 dots around it, that's all I really care about at this point.
Could I make like a fun pattern if I wanted to?
You could, although the important, it makes sense that there's like 4 sides, although if you have 7 dots around chlorine at this point, I really don't care. Okay?
So I
Abby, go ahead. No. No. Again, it's like if you have the open spot like up here, that's fine. I don't care, right? See how like this? Oh, that's fine. Like this?
Wait, is there a lot of
Yeah, there has to be a blank spot here because in this case there's only 7, right?
No, I mean like one side. Does the lava side have
Not necessarily, although a lot of times like what we do is we'll kind of start at the top and sort of go. So if I was writing oxygen, and I'm going to write this in dry erase marker so it's not going to show up on the recording, but if I was doing oxygen, I would go here. I know I have to put 6, right? So what I would do is I'd start here 1, 2, 3, 4, 5, and 6. Okay? If you put 2, 2, and 2 and leave this side completely blank, technically that's right, although you'll see a little bit later on, writing it this way helps with the next step of what we're going to use the Lewis structures for. Okay? All right. Good with these Lewis structures. Okay? So we've already established that elements in the same column have the same number of valence electrons. So, look at your periodic table. Okay? Lithium is in the first column of the periodic table. And when we drew our Lewis structure for lithium, how many valence electrons did it have? 1. So every element in column 1 has 1 valence electron. Column 2, how many valence electrons will elements in column 2 have? They will have 2. Next, we're going to skip the transition elements. We're not going to worry about columns 3 through 12 in this class. Okay? In chemistry, you'll talk about them, but the pattern isn't nice and defined like it is for all the other elements. So we're not going to worry about that for now. Okay? Column 1 has 1 valence electron. Column 2 elements have 2 valence electrons. Skip this here. 3 valence electrons for column 13. 4 for column 14. 5 for column 15. 6 for column 16. 7 for our halogens. And then 8 for our noble gases.
Oh my God.
So the last Lewis structure that you have, right, is neon. Neon is in column 18. It's a noble gas. So it's going to look like
Is
this.
that why they're so stable?
Okay, that is why they are so
They have a
stable,
little shell.
which we will talk about here in just a little bit.
Oh my gosh, I'm slowly going to forget it.
All right, good so far. We okay?
Yes.
All right, now, why is the number of valence electrons important? Because, okay,
It's important for bonding.
it's important for bonding. Or we say that the number of valence electrons determines the chemical properties of an atom. Chemical properties is a fancy way of saying what does this element bond with? What does this element not bond with? And if it does bond with something, how does it bond? Chemical properties is a fancy way of talking about bonding behavior. Okay? The valence electrons determine what something bonds with and what something doesn't bond with. Okay? And the magic number when we're talking about chemical properties is 8. Up until this point, when we have talked about the number of protons and electrons that an atom has, what's always been true about the number of protons and electrons that an atom has? They're the same. Because equal number of positives and negatives. What we find out is that in terms of potential energy for an atom, having 8 valence electrons is more important than having an equal number of protons and electrons. 8 valence electrons is more important than an equal number of protons and electrons. Okay? For example, all right, let's go back here. So let's take a look at fluorine because it's the easiest one. Okay? We've already established how many valence electrons does fluorine have? 7 valence electrons. How many does it need to get to 8? 1, right? We talked about that these 2p orbitals can fill 6, or they can hold 6 electrons. There's already 5. It needs to pick up 1 more to get there. Okay? Same is true of chlorine, right? 7 valence electrons, they're just 1 level higher. It's looking to pick up 1 more to make it full. Here's oxygen. How many valence electrons does oxygen have? 6. We said this number can go up to as high as what? 8. So, right? Or sorry, this number can be 6, right? So 2 plus 4 right now is 6. How many more electrons does oxygen want to pick up? 2 more, okay? I'm going to draw 1 more electron configuration up here on the board because it's important to this discussion. Let's go ugly brown because that will stand out nicely. Good. Oh, let's go green. I haven't used green yet. Oh, I have used green. My bad. Never mind. We'll go with pink. Okay. All right. Sodium. Sodium has 11 electrons total. There's the electron configuration for sodium. Okay? Hopefully I wouldn't have to draw it for you to answer this question, but how many valence electrons does sodium have? 1. It's in column 1, so you should be able to tell me that. Now, here's where things get a little different from what we've talked about. How many valence electrons are atoms looking for? 8. Here, right now, the highest level that sodium has an electron in is the 3rd level. But there's only 1 electron in that level. So one option that sodium has is to pick up 7 more electrons to fill the 3rd level. However, if it were to pick up 1 extra electron, okay, right now, the way it's written, it has 11 protons and 11 electrons. Yes? If I put another electron here, now how many electrons would that sodium atom have? How many total electrons would it have? It would have 12. But it still only has how many protons? It still only has 11 protons. So what charge does it have now?
It's negative.
It's negative. Do other electrons want to come near it if it already has a negative charge? No. Negatives don't like other negatives.
Everyone knows that.
So picking up 7 extra electrons is really hard. Because once you pick up 1 extra, it's hard to even get the second one. Okay? Does that make sense? All right. But sodium has another option. Okay. It has 1 valence electron. Let's say that it got rid of that valence electron. It gave it away to something else. How many valence electrons does it have now?
Mojo.
It has 8. They're in the 2nd level, but it's got 8 now. Okay? So what we find is that getting to 8 depends on which way you go. Some atoms like to gain electrons to to get up to 8 valence electrons, but some atoms will lose electrons to go back down to 8. If we look at the pattern down at the bottom, this would be a description of the number of valence electrons as we move across the periodic table. Excuse me. 1, 2, 3, 4, 5, 6, 7, 8. That gives us to the noble gases. We go down to the next column, or sorry, the next row, and the next row has 1 valence electron at the very, very far left, right? So if you're already at 7, it's easier to pick up 1 to get to 8 than it is to go all the way back down to this 1, right? But if you have 1, it's easier to lose that 1 electron than it is to try and pick up 7 more. 8 is the magic number. How you get there depends on how close you are. Okay? Good? What if it's 4? Good question. What we'll find is that 4 elements that have 4 valence electrons get to 8 in a different way than gaining or losing, which results in a different type of bond, which we'll talk about next week. Okay? We find that atoms get to 8 valence electrons in a couple different ways. Ones that have 4 go about it a different way than ones that have 7 or 1. Okay? All right, good? That's a good place to stop. We'll pick it up from there tomorrow.
Wait, that's not your joke.
I don't have a joke.
Your life.